Okay, so today we're going to talk about higher inductive types. But first, I want to finish saying a couple of things about equivalences. So let's recall some basic things we were doing last time. So last time we discussed this idea of property versus structure, explaining that you don't want to ignore structure where there is structure present because it's very likely to get you confused. And then, because in homotopy type theory everything is a construction, you might get structure where you didn't see one in traditional mathematics using sets. And in particular, we had the example of groups and how there were two ways of getting the associativity proved between reassociating four elements. There were two ways to do it, and then there was a question of whether those are equal. Anyway, the moral of the story was that you need to pay attention to which things are property and which things are structure. And for instance, to properly define what a group is in homotopy type theory, you have to say that, well, it's what you think it is, but the carrier needs to be a set. It has to have homotopy level 0, because if it has higher homotopies, then it's not a group, then it's something more complicated, because you will care about all, for instance, all possible homotopies between the two ways to reassociate four elements. And so that's not a group, because that's not what algebra is about. That's some other branch of mathematics. It's not what group theories do. Then we also discovered that the naive definition of isomorphism isn't the one, that one doesn't give you property. So this was given f from x to y. We defined is iso of f. We said, well, what is an isomorphism? We said, well, an isomorphism is a thing which has an inverse. And so we said, okay, so to be an isomorphism, the space of proofs, the space of evidence. So the point of this space needs to be evidence that f is an isomorphism. What is that evidence? It's a G, but it's not just this G going in the other direction. It's a G together with two paths. F is the identity on X. And then we discovered that this is not, in general, a proposition, while there is, you can show using function extensionality that G is unique. There was a question of whether these guys here give you a property. Namely, there could be many ways in which F composed with G is the identity. And so we identified a better way of saying that something is an isomorphism, namely equivalence. So this one says there is a G which is a left and a right inverse, but you could also say inverse images of points are contractible. That was another way of saying it, which is for every y is contractible, the homotopy fiber Fy, where of course, again, this doesn't mean that at every y this happens to be contractible. There's a continuous choice of such contractions, so that's stronger. Where, what is this thing here? The homotopy fiber. It's what you would naively write as the inverse image of f at y, and then because it's impossible to write things which aren't homotopy invariant, you end up writing down the homotopy fiber. So it's those x's in x such that f of x equals y. And this one, the point was that this one is a proposition. So is prop is equiv f. So having a two-sided inverse isn't a property necessarily, but having all homotopy fibers contractible is a property. And so this means that if you want to think of being an equivalence, so F can only be an equivalence in one way. That's the point. But it can be an isomorphism in many ways, not because it has many inverses, but because these guys here can be multiple, right? These guys here may not form a proposition. Okay, and so I just wanted to point out that there is a third way. Oh, so then when we define the space of equivalences from X to Y, so if you have two spaces X and Y, then you said this, by definition, is those F's from X to Y such that F is an equivalence, and we discovered that then you have an inverse, and you have composition of equivalences, and you have reflexivity, namely the identity map is an equivalence. Okay? I would just like to show that there is another way, because if you think about, these are all ways of saying that something is isomorphism or bijection. This one is saying has an inverse. This one is saying, in a slightly fancy way, it says the inverse image of any point is a singleton. That's what it says. And if you think about it, that's also a way of saying that something is a bijection. But here's another one, by invertibility. So is by invertible. This one says there is a left inverse to F and there is a right inverse to F, but they need not be equal. So you say, there is a G from X to Y such that F composed with G is the identity on Y. G is from Y to X, thank you. And there is also an H from Y to X, which is an inverse the other way around. Now, why would you think of this as possibly reasonable? Because classically, F, what does this say? Well, if F has a left inverse, how can F have a left inverse? If it has a left inverse, it's epi. It's a split epi. So F is going to be an epi. So it's going to be onto. And if it has, sorry, this was a right inverse, yeah. If it has a left inverse, then it's going to be surjective. Am I doing this right? The other way around? Let's be careful. Okay, here, what I know is G is injective. So F is, right? So F is surjective here. This one says F will end up being surjective if you just read this set theoretically. And this one will end up saying F is injective. Okay, so surjective, injective looks like a reasonable definition. So is this one okay? So you see, this is what people would have naively expected. This is what Vladimir Voevodsky came up with. And then I think it was probably Joyal that at some point, I seem to remember, like we were sitting in the lecture room and he said, oh, but this as well. So what he saw somehow with his magical powers is this. He said, but isn't it going to be the case that is prop is by invertible F? And yeah, this one is also a property. To have a two-sided one, to have a two-sided inverse is a property. And in fact, as it turns out, then, this is equivalent is by invertible F is equivalent to being an equivalence. So this one is also okay. You could use this one. And there is a third one, which is half adjoint equivalence or something like that. I think it's what it's called in the book. There's a third one look at the hot book, it's there. I'm not going to go through all of them. The point is that we are, because our universe is richer in structure, we're not killing it off. This structure is playing a role. And this, in fact, it's playing many roles when you discover the extra structure. One role it plays is that it gets in your way, because things that used to work don't work anymore because the structure is there. So sometimes you need to be careful to make sure that it isn't there. But also it gives you opportunity to study new things that you couldn't study before. So if we just do ordinary algebra, we're not going to ask how is this associative, but now we can ask how is this associative, and we should discover some sort of homotopically richer groups, and in fact people have done so. So these are interesting things, but of course there's more of everything. So for instance, now we have here 3 reasonable ways of saying that something is more or less a bijection or isomorphism or epimono. You know, it's all the same in set theory. Now it's not the same because this extra fidelity is making a difference. I just want to also show you one way of how now the equivalences get used. And so what we're going to do is, let's do a basic concept namely homotopy pullbacks. I could have, there's a number of examples I could use, but this one is kind of typical and just complex enough that you get to feel how the equivalence is going to work, and how you can then use it in many other ways. In this way, you can use it in this way to express what is usually expressed by universal constructions in category theory. So a pullback is a limit in category theory. A limit is something that has a certain universal property. A universal property is always of the form for any data like this, there exists a unique blah blah blah. Okay, that's what a universal property usually is. Now you look at it. So what is okay? So let's just first write down the usual pullback. Okay, the usual pullback. The usual pullback says if I have x, what is this? Z, y, f, g. What's a pullback? Well, a pullback is going to be some configuration. It's a configuration like this. Well, maybe this square here, I should remove it right now. And then it's a configuration of some sort. Okay, what is the thing that happens? The thing that happens is, so we have a thing, we have a configuration P, such that for all other configurations, if you have another configuration like that, by the way, this needs to be a commutative square. If the outer square is commutative, okay, so if I have another commutative square, there is a unique thing going here, right? So what is the form? It says we have P, P1, P2, and let's get used to these things. Let's start giving names to this. The fact that this commutes, let's call this alpha. Okay, so we have alpha. So it's a configuration like this, such that for all such configurations, we get, now how are we going to write there exists exactly one? How are we going to do that? How do you say exists? Because now we want to say exists exactly one R here, right? So traditionally you'd say, well, there exists exactly one R such that blah, 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 blah. But now we want to say this in homotopy type theory. something needs to be contractible. But then, if something needs to, okay, so this is going to be of the form pi such configurations u, v, b. Something needs to be, something is contractible. It's starting to look like that. But if it's starting to look like that, now what it's saying is maybe we can get it in the form, because now it looks like for all points, something is contractible. If only the something maybe can be put in a form where it's a homotopy fiber, then this is saying that something is an equivalence. To be an equivalence is to say something is a homotopy fiber. So all homotopy fibers are contractible. So that would be a good attempt. And so we can actually get at that. So let's see. Let me show you how this is done. Okay, so now we do pullback. So now we do homotopy pullback. So question mark here. Homotopy pullback. I would like to point out that this is, I find this super cool, because this is, we are replacing a universal property with a homotopy theoretic notion. We're packing everything like homotopy. So there is a slogan in type theory. Type theory eats itself. Okay. So in general, when you have a formal system and you say that the formal system eats, a theory can eat itself. That means the theory can express itself. For instance, Gödel showed that piano arithmetic is rich enough to express the syntax and provability of piano arithmetic. One of the standard exercises in type theory is to try to formulate type theory inside type theory. So this, what we're doing here is homotopy theory eats itself. At the end of the day, you don't need anything. There's just homotopy theory, because you replaced category theory with things like contractible and so on. And so now, you feel self-righteous and that you have achieved the goal. There's just homotopy theory. Well, it's not quite homotopy theory, it's homotopy type theory. Okay, what is a homotopy pullback? It's this thing, but you need to say it using paths and types and so on. Okay, so we are given, what are we given? Well, we're given this f and f from x to z, and we're given g from y to z. Okay, and now what is a pullback? Let's see. So now we can consider such configurations. Here you just consider configurations. In homotopy type theory, you have to make a space of configurations. So let's call these things commutative squares where g and f are fixed. So I'll call that a squares, okay, over f and g. So I want to describe things that are like this. So what is that? Well, that's going to be, first of all, a type Q, and then there's going to be U from Q to X, and then there's going to be a V from Q to Y. And now I need this. Well, what is this? That's a homotopy. Okay, so that's going to be a homotopy. So I also need to know that f composed with u equals in z to g composed with v. That's what one of these configurations is. Now we see that I have with these arrows here. Okay, so now let me show you something. Given, so there's something called, I'm going to maybe slightly, you can pre-compose, yes? Something wrong?
Yeah, is this of Q to Z?
Which one? Q, yes. Which one is from Q to Z?
The last equality.
The
little z, no, the little z.
What do you want me to write? Okay, so do we agree that this one is FU?
At one type.
Oh, yeah, okay. Yeah, that's why you don't write these types down, because you get them wrong. Okay, so that's why in category theory you don't write anything down, because you could get it wrong. So here we go. So now we want to say something, okay? But here what you observe is usually what you do is you do it the other way around. If I give you Q, if I give you one of these R's, okay, if I give you one of these R's, if I already have a square, okay, so let me write it, let me draw it. If I already have a square, that commutes like this, and now I come up with just some other R and some arrow here, let's call it little r, okay? If I have such an arrow, then I can make a new square, because what I do is just compose RV and RU, okay? So what does this mean? Given, so let me write it down. So this, I'll call this whisker. What does whisker take? It takes, so it takes a type R, it takes an arrow R, okay, let's go. Okay, it takes a type R, it takes a square, it takes one of these squares, so everything. Q, U, V, and this needs a name now, so let's call it beta. It takes a square. Okay, and so given this, and like this, and R, from R into Q, then it gives you a new square. And this new square is still over F and G. Namely, what does it do? What does this whisker do? Okay, it takes R, Q, U, V, B, R, takes all the data. What square does it produce? Well, the new square is this one. Is here you just have U composed with R, and here you have U composed, V composed with R. And then this, of course, will commute, and this will commute by reflexivity, and then you can patch these three paths together into one path that goes like this. So this is going to be, the new corner is R, this arrow now is going to be U composed with R, this arrow is V composed with R, and then you have here some beta, okay, which showing that this commutes here. So this was my, no, sorry, this one is beta. I already have beta, so beta prime patch together things in star. Yeah, some exercise in working with paths, that if you have these things that you can do it. So, okay, so what did we get? So we see you do the easy direction. If I already have an arrow, it's easy to get another one. And now observe that, in fact, we now have, so now, what is a pullback? Okay, so now we can say, when, so P1, P2 alpha, suppose this is one of these squares, what does it mean for it to be a pullback? If it's a pullback, let's go up here, if it is a pullback, then given any R into it, I can create a new square, but that is going to give me all the squares. Every square arises like that. See, that's the point of the pullback. The pullback says, if you have any other square, Q, around here, you could have gotten it as whiskering with R. That's what it says, in a unique way. And that's where the equivalence comes in. So it says, this is a pullback when the map, let's see which one. You say we are going to whisker, and we're going to whisker with, here we're going to use, okay, so Q is the one that is in the inside, so this one needs to be P, and U and V need to be my P1 and P2, and I'm using my alpha, okay? So if I, and let me fix this R here, okay? So if I leave the last one out, what will I get? If I leave the last one out, that means my whisker has everything fixed except this argument R. So this is something which takes arrows from R to Q to squares over Fg. So, right? R to P now, yes, thank you. It's, if I fix all the arguments, then this thing here will become something that takes the missing bit, which is this R. And once you have the R, you can construct a new argument by simply recomposing like that. Okay? This one needs to be an equivalence. So for all R, this thing is an equivalence. And that's a way of using equivalence to express that something is has a universal property. Let's see why is that. Okay. So first of all, we started with a valid configuration. So this P1, P2 alpha is in fact something that commutes. It's a square. Okay. Now what does this one say? This one says, okay, obviously if I have a little r, if I have an r like here, if I have an r, then the whiskering gives me a square. But what does it mean for this to be an equivalence? Well, for this to be an equivalence, it means that its homotopy fibers are contractible. What does that mean? If I take any square here, its homotopy fiber is contractible, which means for any square here, for any square, there is a center of contraction, is this one, and all other ways of doing this are equal to it. So that's uniqueness. The fact that, so when you say that it's contractible, the homotopy fiber is contractible, it will immediately give you the existence of R and its uniqueness. And it will do this in a homotopically sensible way. So that's important. So I think for a homotopy theorist, this should be interesting because it's sort of discovering homotopy where you don't necessarily see it usually. Usually this is not this place here. You wouldn't think necessarily of doing it this way. I'm not saying nobody's ever done it. But when I hear what I hear of homotopy theorists, they would use homotopy fibers as a, well, as a very common, homotopy pullbacks. It's a very common device in homotopy theory. But it sort of properly sits more, it's more like part of the technique. It's not part of the subject matter. Here I am I'm making it subject matter of the subject I'm studying. As I said, I want to eat, the theory to eat itself. I think computer scientists and like logicians who formulated these things, I don't think we really know what to do with this. What I think is going to be exciting is when some homotopy theorist who really knows homotopy theory, because I don't, will come around and will do something crazy with this that will be really difficult to follow. But I think that's when it's going to become maybe interesting. So right now I'm just sort of observing a slightly interesting piece of formalism, but you need to do something interesting with it. Okay, so now let's go to the subject proper of our lecture today, which is higher inductive types. Now, higher inductive types, so far, if you think about so far, what types can we actually construct? Well, we said, okay, we have the natural numbers and the booleans and 0 and 1 and products and sums and path spaces. However, this isn't going to get you far because the natural numbers, all the basic types that we have are kind of zero-dimensional stuff. They're very disconnected. Natural numbers, they're sets. They don't have any interesting higher homotopy. And you can show that being a set is preserved by sum and by product. So maybe the path spaces can get you some slightly interesting types. But even that is not the case. So as it turns out, so we really do need new forms of construction because the forms we have so far are insufficient from a homotopy theoretic point of view. For instance, it's going to be really sad if we don't have the circle and if we don't have suspensions and spheres and you want like everything, you want CW complexes, you want the whole thing because then the subject is going to actually give you some substance. Otherwise, it's like doing the topology of discrete spaces. You know, how interesting can that be? I can tell you how interesting that be. That can be as interesting as computability theory. So now your opinion may vary as to whether that's interesting or not. I think Davorin understands what I said. I don't know if anybody else. So I'm not going there. Okay. 2. Before we do higher inductive types, we have to do a little bit of ordinary inductive types. We already did, but let me repeat or introduce a little bit of inductive types. Now, I'm going to just do one example because on the advice of my PhD students, I shouldn't do the general theory. But if you want to do the general theory of inductive types, in the hot book and in various other places, you look up the thing called W types. This is also called well-founded trees. But we are just going to do binary trees so that things don't go completely general and crazy immediately. In general, when you have an inductive type, so maybe I do say this much. When you have an inductive type, it's a kind of a very, very special free algebra. So in general, when you have a free algebra, what you do is you give yourself some constants and operations and relations right? Equations. Like when you do a free, if you do, say, a free ring generated by some elements, let's say free commutative ring with unit generated by x and y, 2 symbols x and y. Well, that means you build all expressions that you can from the symbols x and y, the constants 0 and 1, and the operations plus, times, and minus. You write down all such expressions, right? Are those the elements of your ring? Almost. X plus y is supposed to be equal to y plus x. 1 times x is supposed to be equal to x. So what is missing is a bunch of equations. So what you do is, if you want to generate the free ring on x and y, on the 2 generators x and y, you generate all expressions, and then you quotient them by all the equations that the ring must satisfy. And then you will get the free ring. Now, an inductive type is exactly like that, but there are no equations. So I could, in principle, study algebra without equations. It's going to be super boring. But there is one example that everybody knows, the natural numbers. The natural numbers are a kind of a very special algebra which has one constant and one unary operation. There's no binary operation. You start just with one constant and one unary operation. You call them 0 and successor, and you generate freely. What will you get? Well, you will get 0, and then the next thing you can do is successor of 0, and then you can do successor of 0. And because there are no equations, these will all end up being different. And that's how you would generate the natural numbers as a free algebra, and there are no equations. So you could let's do the same thing, but let's have a constant and a binary operation. So that will generate trees. So here we go. This is the wrong pen. Okay, so trees. Binary trees, to be precise. Okay, so the generators. So I'm going to describe a type, the type of binary trees. So it's a new construction. So you say T is a type, and you call it the binary trees. There is, of course, the formalism itself doesn't tell you why they should be trees, but I hope you can recognize that they are. Okay, now we have the constructors. So the constructors are, well, there is something called empty, and it's a tree. And then we have one binary so that's my constant, and I have one binary operation. So I'll call the binary operation node, and I'll say, well, it's something that goes from tree cross tree to tree, because it takes 2 trees and it puts them together into a big tree. Namely, you take the left subtree, the right subtree, and then you put a tree together.
Formation is 3.
Now it's a 3. Okay, so let's have 3. I'll write 3. Okay, there we go. So this already tells me that I have a bunch of elements like empty or node of, empty, empty. I'm too lazy to write this legibly. It's much better to draw them. If you already have a tree, T1, and another one, T2, then you can put them together and you get a new tree. And this representation is very suggestive. But now we want to say that this is freely generated. How do we say freely generated? Mind you, you have a strong urge to say something like this. The type tree contains only those elements that you can get in finitely many steps using the operations node and empty. This is a very natural thing to say. It's a bad idea. It's very natural, very suggestive. If you go down this road, you're going to write thick books about the philosophy of mathematics and you will not get anywhere. You need a better way to do it. Why? Because it's ultimately going to be a bit circular. Because what I will ask, what does it mean that you do it in finitely many steps? And then you will say, finitely many steps. Okay, but the notion of finitely many steps itself is inductive. No steps is inductive. And if I have already made some steps and then I make one more, that's also finitely many steps. And then you try to break this circle, you have to break it the right way. So to break it the right way, you need to say that you need to understand what freely means. Freely means you impose as few constraints, or you do it as economically as possible. As economically as possible is a notion which puts this type of trees into relationship with what else there is. Okay? You need to express what relationship the type of trees has to all other types. The natural numbers are inductive because they are the initial algebra for zero and successor. So what we need to say, so this freeness business, you express so there are now different ways to do it. In algebra, you express it by saying it's the initial algebra. That's one way to do it. In type theory, or in category theory, you would say it's the initial algebra for some functor. In type theory, what we do instead is we explain how to construct sections over tree. And this gives you everything at once. It gives you the initiality and the required properties. So you always have and this is called an induction principle. The induction principle specifies, it characterizes sections on trees. So it goes like this. It says, okay, so we're given, so there's some data, and then with this data we can construct a thing. So first of all, we have a dependent type over trees. It's always going to be the same. So you have a dependent family over trees. And then it explains that a section is always built by induction, so by steps. Okay, so the induction principle for trees at this P is going to be something which says, okay, you give me the base case, so P of empty, and you tell me how to get my section for a node if I already know what the section is doing on the subtrees. So in addition to this, or maybe I can write it like this, in addition to this, you tell me, given any two trees, T1 and T2, these are the two subtrees. Okay, suppose I already know how to get an element over T1, and if I know, okay, so I need the following. I need a procedure. So given this, I need P of node T1, T2. Okay, so given the base case and given a way of making a section on a slightly bigger tree, like picking something in the section on a bigger tree, if I already know how to pick on this on the immediate predecessors, given all this data, then I get a section. And this has both a geometric reading and an E reading as an induction principle. If you read this as an induction principle, this is the base case. This is the base case. This is the induction step. Why is this the induction step? This says, given any two trees, suppose the induction hypothesis holds on those two trees, then it holds on the slightly bigger tree, on the successor tree. You just need two induction hypotheses because each tree has two immediate predecessors. You need both. In the natural, if these were natural numbers, then you would just have one. Okay, that's the logical reading. Later on, when we do higher inductive types, you will see that that we have a distinctly geometric reading. But there is still something left here, namely, so the induction principle is that there is a thing like that, and we also need some equations. The equations say that if you take essentially what they say is, if you take the consequence is this: if you have a section, you take it apart and put it back together, you get what you think you get. Oh, well, maybe we need to be careful. Here are the equations that I care about today. So if I say for the empty tree, I want U, the induction step is done using F. That's the U in here, that's the F in here. Then when you apply this to the empty tree, you will get the base case. And the other one says, and if you do it to a composite tree whose sub-trees are T1 and T2, then this is going to be, okay, this one I want like this, so judgmental equality. This one I want like this. So this one you will compute by using F. You will actually, your section is built using F. It's not built using magic. It's built using this procedure that was given here. So that will be F applied to T1 and T2, and then the recursive calls. Okay, so now it gets hairy. Int 3p u f T1 and int 3p u f T2. It may look hairy. Speak to any functional programmer and they will just nod their head. Yeah, this is how you define functions recursively on a tree. So this is saying a section on a composite tree is built from the induction step. You use the induction step to build it, not some other arbitrary thing. Okay, so this was now an example of an inductive type. And the thing that is important is the form. Okay, so what is the form? The form goes as follows. You say, I'm going to have a type. That's a formation rule. Then you give yourself some constructors for the points. Maybe you give yourself some point. I mean, it's always a good idea to give yourself some points, I mean, to start with. So you maybe have some constants or some base points that you could start with. And then you give yourself some operations that give you even more points. So like node gives you more points. Given some points, gives you even more nodes, or successor. And then to say that this is inductive, so you secretly want to say there is nothing other than the things I can get using node and empty. But if there is nothing other than the things you can get using node and empty, then it should be possible to describe a section out of a tree by explaining how to build the section on the base points and what to do when you use an operation to get a point. And so this is precisely what this is. It says, okay, if this really is inductive, then if I tell you how to do it for the empty, I tell you how to do it on a composite tree. If you already know how to do it on the parts, then you know how to do it. And this is a funky way of saying that it's the least or the most economic such thing. So now what we're going to do after the break is we're going to make another step, which is other than allowing, see, these are point constructors. They give you points. This is a point in tree, and this gives you even more points. What we will allow is we will say, but you can also have path constructors. You can also throw in some paths. But then we need to figure out what the corresponding induction principle is going to be. But that's what we're going to do. But first we have a break.
May I comment on
Yes.
the homotopy pullback?
Homotopy pullback, yes.
Yeah, so what you wrote is precisely what the homotopy theorist would think. Because what you expressed is the fact that the pullback functor is the right being and the limit functor is the right adjoint to the free functor which associates the object to an object, a diagram of which you're taking the limit.
Right, of course. I mean, where do you, yes, so just for the sake of the recording, Yaka is remarking that this is precisely what homotopy theorists would think is going on. And
That's
yes,
right.
of course, the homotopy type theorists just copied this stuff from, I mean, they did the obvious thing, right? If you have a little bit of experience with pullbacks and homotopy pullbacks, then it's not going to, once you get used to this idea of equivalence, it's not going to be super hard to figure this out, because the natural process you will undergo is precisely the one I was saying. You will first try to write down for all exists. Actually, for all exists exactly one, but you have already been burned with this for all exists exactly one in previous cases where you got your isomorphism wrong, and you know that you should be using contractible whenever you see this thing. So you know that you need to be shooting for something is contractible, but a very nice case of something is contractible is all homotopy fibers of something are contractible. So what is it? Well, it's the homotopy fibers of this whisker business. And so,
No, it's
yeah. What I think is, it's not, of course, it's not amazing that we have written this down, because we just transcribed ideas that existed already in many shapes and forms, formal, informal, all of them. You can find them in category theory, in homotopy theory. What I think is a bit, what I think is interesting is that it's not taking a lot of technology to get to this point. I'm using bare bones formal system with pi's and sigmas and identity types. I'm not building up years and years of topology and analysis to get to this point. I'm just doing it directly. This is important because it tells me that if I can make this formal system into a useful tool, then I can have this immediate mode of expression where things are not encoded in a complex way. And that always pays off. You know? Arguments in abstract linear algebra can often be an order of magnitude clearer and shorter than the corresponding thing that is expressed in terms of, say, matrices and determinants. You go crazy, guys. So it's like the hope is that it's going to be a bit like that.
No, I mean, it's definitely it's easier to comment on it when someone has done it before, you know. But now when I've seen it, it's natural.
Right.
Just the adjoint functor principle.
Yep. Okay, break. Okay. Finally, we're getting somewhere. Higher inductive types. We're going to, so the idea is as before. Let me see. I'm first going to have a philosophical discussion, then I'm going to show you the example, because there is something going on here which I think is interesting. Inductive types are about throwing in a bunch of points, but these points don't satisfy any equations. It's like algebra without equations. You just have the operations and you build stuff and you get a bunch of points. This is a bit boring. There are many examples where you want equations. I mean, algebra being the obvious one. If you try to create the free, say the free abelian group, what's the free abelian group? It's a trick question, but what is the free abelian group?
Which generators?
No generators. On empty set of generators. It's the trivial group because it's the empty set of generators. But on one generator, it's the integers, right? But if you start creating them using inverse and plus, so minus and plus and 0, then you will have lots and lots of points which are the same element as I was explaining earlier, because let's conveniently call the generator 1, okay? So 1 plus 1 is going to be the same element as 1 plus 1 plus 1 minus 1. So you want some equations. How do you get the equations in? You quotient, okay? And this is a very general phenomenon all over the place. You make a space, you make something, you got too much stuff. You want some of the stuff to be equal. What do? You quotient. So algebra is like that. Completion of a metric space is like that. You want to complete a metric space. See, you took everything they told me, you were not coming back, so we started. I'm just explaining, a common situation is that you generate points of a space, and then you want some of them to be equal. And quotienting is the thing you use. So another example, completion of a metric space. How do you complete a metric space? You take the space of all the Cauchy sequences. But that's not good. Some of them ought to be equal, because some of them, morally speaking, converge to the same point. So you quotient. And this is present in many, many places. Everywhere you look. This is a very common thing. There is something really bothersome, both from a structural point of view, namely that the two steps are of a different kind. First, you generate something. You create all expressions that the algebra is supposed to have, or you take all the Cauchy sequences. The first step is, in its nature, growing. The second step, quotient, is an animal of a different kind. A quotient is a colimit. And so it's putting things together. And this mix of generating followed by quotienting is often presents really annoying technical difficulties. This mix complicates matters in many, many places. And so then people spend years in books figuring out how to lift from a quotient and how to avoid this or that, or what do we do now if we want to repeat this, and then we're going to have everything mixed up, generate quotient, generate quotient, generate quotient, what the hell is going on? So it is overall an important technique that shows everywhere, but is also technically complicated. So it would be much nicer if both steps were inductive in nature. But can we do that? Well, you can't do that in ordinary set theory, where you simply have to make things equal. If you want to make things equal, you have to make them equal by quotienting. However, in homotopy theory, we don't really make things equal. Things are not really equal. There are paths between them. So we have the following possibility, that we're going to have a wholly inductive construction, because what we do is we can throw in points and operations that get us more and more points, but then if we want them to be equal, we don't quotient them, we just say, oh, now we throw in some paths. And so then we throw in more paths. Now, this is going to also have its own technical details that you have to get right, because the throwing in the paths is going to create even more paths. If I throw in a path from A to B, and then I throw in another path from B to C, I will also create a path from A to C. And so now if there was some previous path from A to C, and now I have another one, maybe I want them to be equal, now I have to make those equal, and la 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 la. So, okay, by the law of the preservation of trouble, I will just be pushing the trouble someplace else. But at the very least, the entire construction will be all of the same sort. It won't be inductive followed by quotient. It'll be inductive and some more inductive. And this can be very beneficial. For instance, I don't know of any construction of real numbers, Cauchy real numbers, satisfactory, without choice, predicative, other than the one that you get in homotopy type theory. This is chapter 11, probably, of the HoTT book. You can see an inductive construction using Cauchy sequences. You throw in Cauchy sequences, but then you don't quotient. You throw in paths between those Cauchy sequences. And you get the reals without any quotient anywhere, and without any impredicativity. So it's just magic. So I find this very nice. But now let's go back to the historical development. The first higher inductive type ever to have been created was in Oberwolfach, and it was the circle, of course, as it should be. So, example, the circle. So this was, so maybe the history here is a little bit obscured, so I might as well say it out. We were walking to the cake place in Oberwolfach, and it was Mike Schulman, Peter Lumsdaine, Michael Warren, and myself. And then when we got back in the evening, everybody else was drinking beer and doing cheese, and Peter was typing in the circle into cock and got about half. I mean, I think he got it right, but then we couldn't prove that the fundamental group of the circle was the integers, which we will do next time. Okay, so higher inductive types. I should also warn you that whereas there is a well-developed general theory of inductive types, the W types is just the simplest kind. There are others. There is no generally developed theory of higher inductive types. This stuff is from 2012-ish, 11-ish, something like that. And so we know of examples. We don't have a good comprehensive theory yet. We have for certain fragments, there is good comprehensive theory, but not for the entirety of the idea. We have here a typical example of a mathematical idea where a technique has been developed. People who learn this technique, when they see one, they know it's a higher inductive type, although it can get scary. There are scary parts to it. But the general theory is a bit still somewhat unclear. Maybe also before we go into these particular examples, if you look at the HoTT book, what kinds of constructions can you make? Okay, circle, spheres, suspensions, all this homotopy theoretic stuff. But then models of ZF are made using this. Real numbers are constructed like this. Conway surreal numbers are constructed like this. Lots and lots of interesting constructions that also go beyond just propositional truncation, which we're going to do. So lots of interesting examples. But let's do homotopy theory. So the circle. We follow the usual pattern. We say there is a type called S1, and we call it the circle. Now we need an idea. Well, the idea is that the circle has a base point. You could try to have a circle without a base point, which would be very interesting, and people do think about these things. But at least for homotopy theory, you want it to be a pointed type. Otherwise, it's kind of weird. Okay, there's lots and lots of constructions that want you to have a chosen point in the circle. So we're going to say that this is the circle. It has a base point and it has a loop. And everything else needs to be generated from this loop. So, constructors. And now, because there are point constructors and path constructors. So, because we used to have just point constructors. So, point constructors. Well, there is a point called B, and we call it the base point. And that's it. So you might be thinking, what's up with all these other points on the circle? They're a little less concrete because they are sort of there in virtue of there being a loop. Okay. But then there are path constructors. So now we are constructors. We are throwing in some generators for paths. Each such generator will generate. See, if I just give you a point, that's it. You don't get another point from it. But if I give you a path, especially if I give you a loop, you suddenly get lots of paths because you can start composing this loop with itself. So here we're going to have another one. So now I tell you what it is. It's called L, and it's something that goes from B to B. It's part of the identity type. And it's called the loop. Very similar way we could define one-dimensional CW complexity. Okay, yes, so you're immediately mentioning CW complexes. After you've seen this example and maybe the next one, which will be, I think, the suspension, then I will ask you how to do the sphere, and you will just probably be able to just tell me how to get the sphere, because you know how to get the sphere as a CW complex. The interesting question will be this: you know how to get the sphere as a CW complex in more than one way. We'll all give you equivalent types. They better do, otherwise our theory is broken. Okay, so now, what can we make out of this stuff? Well, for instance, we can make lots of loops. There is a loop called L composed with L, which goes from B to B. That's like going around twice, and so on. But now we want to say there is nothing else, and this is free construction. It turns out that to express the induction principle properly, we need a little bit of preparation, because we need to be able to speak about, you see, it's going to be about sections, and it's going to be about paths in the sections also, because now we have path constructions. So we need a little bit of preparation, which we haven't done so far, before we can do the induction principle. Okay, and so the preparation is, first we need this notion of path over path. It's something that's quite natural from a homotopy theoretic point of view, but we never mentioned this so far, and we should explain it. The idea is quite simple. If I have a fibration, right, so there's some space here over this thing, whichever way you want to think of this. Okay, and so then you have a path here, P, and this is a fibration P. So here's the fiber P of X. Okay, I'll just write it like this. Here's a fiber P of Y. I should have this idea that if I have U over X and I have V over Y, that then there is such a thing as a path over P, that I ought to have a path, say Q, which somehow projects down exactly onto P. That's how you usually think of it. When you have fibrations, you lift a path, okay? When you lift the path P, you get the path Q upstairs, but it's not just any path, it's over P. That is to say, when you project it down, it goes into P.
But we prescribe both endpoints?
Well, now, whether these endpoints are prescribed or not, that's up for discussion. We can prescribe both, neither one. But first, we just need to know what it is to have a path over P. And why am I emphasizing this? Well, because where does this Q live? So one way to say this is to say, well, Q, the way this picture is drawn, it lives in the total space. So maybe this needs to be in the total space. Q is a path in the total space, in the sigma of P. And that would work perfectly well, but there is a better equivalent way of doing this, which is like this. You can say, aha, but if I have this path here, I can transport U over, see, I can use P to transport U over here and take a path there. So path over path, let me just first say let me just specify what I want. Okay, so what we have is we have P, which goes from some type A to U, and then we have X and Y in A, and we have a path P, and we want the space of paths over P. So what will this be? This will be something like this. From U to, right? Oh, we also have U in P of X, and we have V in P of Y. From U to V. That's what we really want. Okay, and this space, we're going to call it, what would be a reasonable way to call it? Well, you would call it like this. You would say, I want a path. So this space is the space of paths from U to V over the path P, but in what? Oh, sorry, can I rename this to B? Because there will be lots of P's everywhere. So all the capital P's become B's. Okay? Like this. In the fibration B, I want a path from U to V over P. The natural way to do this would be to just now write down what? You would write down it's a path in the total space such that when you take the projection down, you will get P. That's what you would write down. It's hairy, can be optimized, turns out to be the same thing as it turns out, because if you have this imagined situation in the total space, you could sort of move everything over to the fiber by. You move the U here, and this path also can sort of move there. You see that there isn't going to be any difference. So what you do is you say, well, a path like that is actually, what you do is you transport along P, you transport U. When I take U over here, so let me draw a picture. I need a bigger picture. Here's U, here's V. I transport, this is the transported U, so here, it's not a bigger picture. And then you take a path here. So, not a very good picture. It's like that. So to have a path over P, which sort of goes across the fibers, you could say, well, it doesn't go across the fibers. Instead, we put everything into the last fiber and take a path there. Okay? As it turns out, you could equivalently move the other one. So it turns out you could instead say, oh, what if I move the other one? Maybe it's the same thing. And that would make a nice exam exercise or a little lemma in the hot book. You would want this to be the case. So we can speak of these paths over a path. Geometrically, it's precisely this picture that you want to have in your mind. Formally, once you start doing the things, you just say, oh, if I want a path over a path, I transport everything to the same fiber and then I do it there. And this is going to rely on some lemma about what the path space of a total space looks like. That's one thing, path over path. The other thing that we need is, remember we already saw that if you have a path, you can map it with a function. If I have a path in the domain, then a function takes it to a path in the codomain. But I need that in the dependent version, and that's called the dependent application, dependent apply. So
that overthinking must be hidden in the transport.
Yeah, of course. Yeah. So what you need to think about, what you would really want to think about is, if I phrase this in the language of the total space, like you would normally, if I show this to a homotopy theorist, they will say, well, it's a path in the total space such that if you project down, you write down that type in homotopy theory, and you prove that it's equivalent to this type. And then you say, okay, it doesn't matter which one. And you can also think about, why is this? Why can I transport U over here and then do paths in here? And you can think of some topological explanation of why that must happen.
That's the action of the path space.
Yeah. And that too, in this other more direct version, would also make, I'm sure, a nice exercise for the students. So dependent application. It's like this. We suppose, again, we have a function, but now it's a dependent function. So we have something which takes, so it's a section, right? So here's A. Here's B, and then we have a section in here. So F is a section. And now if I have a path here, P, can I lift it to a path over? That's what I want. So does F take this path here up there so that this path here is over P? So what we want is this. And this is sometimes called, so given path P from X to Y, want something that is f of P, okay? And this f of P needs to be now what? It needs to be a path over this. So it needs to be an element of, okay? So what will be the endpoints? F takes X to f of X, Y to f of Y. So the endpoints will be f of X and f of Y. This is all happening in fibration over B, and it's over P. Okay? So that's what we want. So how do we get it? Okay? Well, let's write down what this is saying. It's saying for all x, y in A, and for every P from X to Y, I want an element of this type. What is an element of this type? Well, whatever it is, I want an element of this type. And now it's saying, aha, so this is, you want something for every path unrestricted in its endpoints, path induction. To construct this guy here, f of P, yes, well, this is f applied to, yeah, x, y, and P. So path induction. So you say it suffices to have this much. And P becomes ref of Z. Can we do that? Sure, we can do that. It's lambda Z refl f of Z. Because reflexivity over f of Z will be over f of Z. So this is the magic of path induction. Okay, end of preparation. Now we can do induction principle. For the circle. Follow the same principle. We have a dependent type S1 to U. So here is P of B. We would like to create a section. So how do we do the section thing? And the thing is, again, well, if the circle really is generated by the base point and the loop, as soon as we know what to do at the base point and how to treat the loop, then we should be done, because that generates the entire circle, so it should generate the entire section. Okay, so we say we want, what does this int do? Okay, so this is the induction for P, for the circle. Okay, let's go. So we say, okay, you need to give me something. You need to give me something over the base. So you need to give me a point here called, let's call it U. Give me something over the base. And then you need to do something with the loop, okay? So you need to give me, what you need to give me is, you need to tell me how to lift the loop. That's the point, right? So what do we expect? So we need this lifting thing. So, oops, right? You told me what how the section lifts the base point. Now please tell me how the section that we are creating is going to lift the loop. After that, if you tell me how to lift the loop, I should be able to lift the entire circle. So, what is this? What is this magenta thing? Well, it's a loop. It's a path over L. So I just say, aha. So if you give me a path over L, then I give you a section. That's what induction does. So what it's saying is more or less, no, not. It's from. Oh, it's from U to U. Thank you. Yes. Here and here is from U to U. There we go. Lift points, lift paths. We're done. That's okay. But we also want some. We now also want some equations. Are there any equations? Yeah. Presumably there are some equations. For instance, now that I get my section, so I will get, see, this will be my section. Well, the section better take B to U, right? It should take B to U. It shouldn't take B to something else. So it should take the base case. It should, on the base case, it needs to act the way in the prescribed way. So if I now say, okay, you're supposed to lift the base point to U, and you are supposed to lift. You're supposed to lift the loop to gamma, and then you will get a section. Please tell me, what does this section do to the base? Well, it better do U. And also, I can do the same thing. So you see, I could also ask, how will it map L? Okay, so this is a slightly imprecise notation. In the book, the more precise notation would be something like app D of int P U gamma L. I'm not supposed to plug in a loop where a point is expected, but I already committed this in up here when I say I apply F to path. Okay, so it's the same thing. So as you can see, even formal people like me also become very sloppy with notation. I think this is a feature of humans, that we can function despite all the ambiguity and lack of proper information. So here we go. This is supposed to be what? Well, this is supposed to be L. Right? This better be L. So now there is a question of whether you want this to be L like this, which gamma. Sorry, gamma. Yeah. So this is gamma, and you can. So these are you would certainly expect these equations. The problem is, would you expect any other equations? And there are some other equations, but given that I have 15 minutes, I'm not going to get into that. The HoTT book has a very thorough section on the circle, which I would hope you are able to read after this introduction. That this is, you need to do things right. Anyway, I hope this idea is getting across. We are just generating, in addition to points, we're generating paths. Let's try another one. Let's try propositional truncation, because we use propositional truncation to say to force things to be propositions, and there's something to be learned in this example. The idea is quite simple. You have a space, you want to connect all of its points with paths, so that there are paths everywhere between any 2 points, because that's how you collapse a space so that it has at most 1 point. So if I start with an empty space, I should get the empty space. But if I start with a space that has a point, I should get a contractible space, because I will connect everybody to death. Yeah? So that's what I want to do. I don't want to say, take a space, add another point, and connect everybody to that point, because that would be a what? Homotopically speaking. Take a space, add a point, yes? That's a cone, right? And after you've seen suspension, of course you will know how to make a cone. And even, okay, so let's see. So propositional truncation. Given a type, okay, we have, and now we say this is a new construction, a thing called the truncated A, which is a type. And now, if you remember, what was it here on the side? with A, we had this map, right, which took a little A, and it sort of gave you the, secretly, think of this as the equivalence class of A. Of course, there is just a single equivalence class, but given A, you get the only equivalence class of the truncated A. So we need this. So this is a point constructor. You see, it's creating points in here, but it's parameterized by A. For every point in A, I get a point. So point constructors. There is this thing called bracket, which goes from A to A minus 1. So if you wrote this as an inference rule, it would say whenever you have A in A, you're going to get this thing. But now we also have to say that all points in A to the minus 1 are equal. So we need some path constructors. And there is one, and I'll just randomly call it P because people usually don't give it a name. What does this one say? This one says if you take any 2 points, let me call them alpha and beta, in this space, they're equal. Throw in, there's a path between them. Now you should worry that maybe we need extra path constructors between these paths. So maybe there will be 2 points from alpha to beta. Maybe there could be alpha and beta that have 2 paths between them, and then that's wrong. I don't want this. I want this space to be contractible. I don't want it to be, like, it shouldn't have any loops, non-trivial loops and things like that. No, it turns out this is enough, because once you kill the paths of dimension 1, the paths of dimension 2, 3, 4, and so on are gone. That's something you need to prove, which I'm not going to prove here. This is what we need. Okay, but now we also need the induction principle. And we're going to follow the same pattern. It says, suppose I have a type A, I have a dependent type from A to U. Okay. Then something. Now, I can write this down. Now, I'm going to write it down. So what we're going to get is a generalization of what we wrote when we defined propositional truncation, but it's not, the relationship between the two is interesting, but let me write it down. Okay, so what does this say? Okay, so this we're given. So what will this int do? The int for P will say, if you tell me what to do with the base points, so there's lots of base points here, and then you tell me what to do with these paths, how to lift paths, then I'm happy. Then I give you a section. Okay, so it wants to have, for every base point, that is to say, for every x in A, you need to give me a reason or a point, lift for that one. Okay, and after you've done this, I also want you to give me, for every path, for every pair, alpha, beta, and for every u over alpha and every v over beta, I want you to give me a path from u to v, so more or less lift this path p alpha beta. You wonder which p is this. This p is this p. Okay, from u to v. There is a path constructor which gives me a path from alpha to beta, and so now I want to lift it. So if you tell me how to map the point, how to map the base points, how to lift the paths, then I give you a section. That would be the induction principle. And I'm going to skip the equation now, plus equation. But it's still following the same thing. It's saying something. Look, one consequence. So how can you pull this off? Look at what you need to do here. Okay? Here you need to do, if you think of alpha and beta as being the same point, this is saying if I have any element u in P, so assume that I took the same point, that beta is just alpha. So this is saying take any u in P of alpha, take any v in P of beta, okay? And then here use P alpha alpha. Then you need to give me a map from u to v. We're sort of seeing that all the fibers need to be propositions. All the fibers of P need to be propositions. We're not quite there. That's why I was saying it's not quite the same. But something's going on. It's difficult to satisfy this. I mean, you can only satisfy this if this big P is very special. Because this big P needs to give you, at least where you're mapping to, needs to give you lots and lots of paths. Yeah? You need lots and lots of paths here. Okay. Last one. Suspension. Topologically, I mean topological suspension. What is a suspension? Well, if I have a space A, how do I make a suspension? I put in 2 points, north and south, and then I connect like that. Right? Okay, so one would think, what's my plan of attack? What will be the points of, what points do I have in the suspension? I have the North Pole, I have the South Pole, I have A in there, so for every point in A, I need A in the, maybe, no? It looks like I have an A in there, and then I put in a bunch of paths. Okay? I have a better idea. I'm not going to put A in there. I'm just going to do this. I will put in North and South, and then whenever I have a point A in A, I will put a path. This is called the 8th meridian. Yeah, I'll do it like that. There's no need really to try to embed A in it, because I will get the same kind of paths going like this. Yeah. I can still maybe think about, so you can think about the following question: does A always embed into suspension? It does. Yeah. So maybe it's going to be an exercise to figure out whether A embeds into the suspension. Something fun is going on, because up to homotopy, maybe embedding A into the suspension is like, I don't know, maybe mapping everything to the North Pole. I'm lying, but like for instance, let's take the cone. If I have the cone over A, the cone is when you have just one of these, it looks like A is embedded in here, right? But homotopically speaking, embedding A down here is no different than mapping A to all of N here. Just map all of A to the North Pole. It's the same thing. There's a homotopy there. Isn't there?
Yeah, sure, but that's the same for the suspension.
Yes, so things are going on. Everything is homotopy invariant, but let us do the construction at the very least. Okay, so given suspension of a type A. Okay, so what do we say? Now, how do you write suspension in homotopy theory with a sigma? We used up sigma for dependent sum. What to do? Well, I'm going to use sigma anyway. Okay, you want something? Okay, I'll like sigma there. It's a more beautiful thing now. This is a type.
It's a main sigma.
Point constructors. The point constructors are that there is a thing called N, the 2 poles, and S. And now we resist the temptation to embed A. We just say, okay, that's it. And then path constructors. Of course, it is very suggestive to draw A like this and then paths between them. Right? So path constructors, well, we need these meridians. So M for every point in A. Actually, I can write it like this. Let's practice this. Given any point in A, I'm going to get a map from north to south. I get, this is A many points from north to south. Any equations? Oh, induction principle. Okay, this one I will leave as exercise, but you follow the same pattern. If, so what do? You say, given P from the suspension of A to U, so what do you want to give? Given a lifting of N, S, and all the meridians, we get a section. This is the thing I want you to actually remember, the inductive nature.
I'm unhappy.
You're not happy because why are you not happy?
So you wanted the circle as a naturally based object.
Yes.
Why isn't it the same for the suspension? Why didn't you do the reduced suspension?
What is the problem that you don't want 2 base points or what?
Yeah. So why didn't you do just an A worth of circles?
A worth of circles.
Yeah, based at a single point.
Based at a what do you mean based by a single point?
It's just the north pole or whatever. The base point.
Okay, so alternative.
I want the reduced suspension.
Well, okay, but do you want the suspension? Or, okay, so what is? Show us what you want. Take one point called N, B, call it B, and then A many circles.
That's right.
Okay, so for instance, so you want a circle like this, C of A for every A in A, or if we imagine something like this, here's A, here's B, you want like that?
Yeah.
What will be the relationship between those two spaces? So first of all, this one is based. You pick one. You pick, like you say, the north is the base.
You have to pick one.
Yeah, but the 2 choices give you equivalent based spaces, so it doesn't matter. Yeah. Okay, something to think about.
So the idea would be to contract one of those meridians to a single point. That's the idea. That's my idea. I mean, I don't know how to do this.
Okay, so if A is already based, then you contract the meridian at the base of A. That's what you want. Yeah. Okay, that would be, in principle, a different construction, which is doable. Yes. Let's just calculate a couple of things. What is going to be the suspension of the empty space? You take north, you take south, and no points between them, so 2. Yeah? What is going to be the suspension of the empty space, which is the suspension of 2? Well, you will take north, south, and you will have a meridian called something, and then you'll have another meridian. So you hope that this is S1. Need to prove it. So this would be already a fairly non-trivial exercise in homotopy type theory to prove that these 2 spaces are equivalent. You can do it. It's in the hot book. It works. It's just that the method of proof this is where a homotopy theorist or a topologist will get slightly lazy, because you have one gluing construction, you have another gluing construction. It's way, way easier to wave your hands and give it to your students than to actually do it on the whiteboard. So here, maybe you want to really do it for the students once and then give them something more horrible, right? And then in general, now if we do, yeah, so now if you do the suspension of S1, you expect this to be S2. But what is S2? If I ask you what is S2, is it going to be a higher inductive type? Yeah, it's going to be a higher inductive type. I wanted to finish with this. What will it be? Well, it will have a base point. It has a base. How do you get S2? What's missing? What do you want to add in to get?
I will do the reduced suspension of the circle.
Okay, you would do the reduced suspension of the circle because that's a cool way to do it. How would you do it with your bare hands? You want a two-dimensional path, right? You want to throw in a surface. So you want to say, these are the path constructors, point constructors, and then path constructors of dimension 1, there aren't any. Of dimension 2, yes, of dimension 2, this is something called surf, which is a two-dimensional path, but from where to where? From raffle B to raffle B. And where is this happening? This is happening in B equals B over S1. Oh, over B, just S2, okay, like that. So point B, and then you sort of have a bubble. You get. Since it's there somewhere, where is it? I'll find it. Okay, I have an animation of this. I'll let you go, but there is an animation of this. So let's see if I can find. The internet seems slow here today, as always. Collections. All. It's probably around here. Alphabetical. Last one. Is it here? Last one. Visual math. Is it one of these? It's not this one. It's not this one. It's not this one. It's not this one. I give up. But this is searching the whole Vimeo now, so who knows? Ah, there you go. Nobody else posted an animation of how to make a hot sphere, so maybe we can show. I can show you this one. Now it's a video recording of a video recording. How long is this thing? 1 minute. Okay, it's kind of long. I think this was my math overflow question to somebody. Okay, we want this. The surface is the H. Okay, so why is it this? Okay. H is a general homotopy from A to B. You pinch together A and B. What do you get? So first, you modify them. You say pinch together A and B. So now it's going to be H is going to be a homotopy from one loop to another loop. Now you contract both loops to the reflexivity path. No?
You have a circle worth of loops now.
But now I do this. I'm okay.
Your circle's worth of loops.
Yeah. But it's a sphere. Okay, thank you.
Why is
Yeah?
in topology suspension of the empty space is
The suspension of the empty space is the empty space? Really?
it's
Yeah.
Well, wherever you saw the definition, it was wrong.
Something like that.
Yes.
You have to amend that.
You.
So you would,
So-
of course, if you cross the empty space with the interval, you will get that.
Okay, I highly recommend avoidance of the kind of sloppiness which gives the border, the boundary conditions wrong. So once you notice that the suspension of when you iterate suspensions and you keep getting spheres, you want to push this also at the beginning. You want to work, so you want the suspension of the empty space to be the 2-point space because that's a sphere. So I would say just fix the definition would be my reaction. How do you even do it so that the empty space gives you the empty suspension? What do you do? How do you break it? Oh, A times the interval and then pinch things together. Yeah, okay, so the moral of the story is don't do that. Don't do that.